If you look at the headlines today, it feels like artificial intelligence appeared practically out of nowhere. One day we had standard search engines, and the next we had algorithms writing code, drafting lawsuits, and generating award-winning art. But the blueprint for this technology is older than color television. Back in 1943, researchers proposed the first mathematical model of a brain cell. By 1950, Alan Turing was already asking a practical, experimental question: can machines think? 7 years later, Frank Rosenblatt created the perceptron, history's first machine learning algorithm. Instead of strictly following pre-programmed instructions, it processed data, made a prediction, and then corrected its mistakes by mathematically adjusting its own equations when it got an answer wrong. Those early pioneers realized that human-like intelligence is a computable engineering challenge, kicking off an 80-year effort to build a brain entirely out of math. This chart shows a classic logic puzzle called the XOR problem. In 1969, critics proved that a single-layer perceptron cannot draw a single straight line to successfully separate these two distinct categories of data points. Because the algorithm was strictly linear, it lacked the complexity to process nonlinear logic. The fallout was immediate. The U.S. government pulled its research funding, academic interest dried up, and the entire field collapsed into a decade-long AI winter. That initial excitement died because the foundational model was structurally flawed. It lacked the necessary layers to simulate complex reasoning. Through the 1980s, a small group of researchers refused to give up. They eventually broke the logic bottleneck using a training method called backpropagation. Here is how it operates. A network makes a prediction during a forward pass. If it fails, that error is sent backward through the system. This tweaks the numerical weights across multiple hidden layers simultaneously, allowing the entire model to learn from the mistake. With basic logic established, these systems needed to perceive the physical world. By the 1990s, convolutional neural networks allowed models to read raw data arrays directly, while long short-term memory networks helped them remember sequences of data over time. But there was a harsh reality. Training these multi-layered systems took an enormous amount of time, and they required vast libraries of digital data that simply did not exist yet. Because of these severe limitations, researchers turned to simpler statistical models, like support vector machines, which required far less computing power and outperformed neural networks on nearly every test. The field plunged into a second winter. Having the correct mathematical formulas was not enough. To truly function, neural networks needed a scale of information and processing power that hardware at the time couldn't provide. The required resources finally materialized in 2012. The internet was generating massive crowdsourced datasets like ImageNet, and researchers found an unexpected hardware solution from the video game industry. A team of scientists created AlexNet, an image recognition system that dominated international competitions by processing data with massive parallelism, running thousands of calculations at the exact same time. The silicon engine that finally powered these neural architectures was the gaming GPU. Because graphics cards are built to execute thousands of simple mathematical operations simultaneously to render video games, they were the exact tool needed to train deep neural networks. This moment proved the stubborn pioneers of the 1980s were right all along. Their algorithms were structurally sound. They were simply waiting for hardware fast enough to run them. By the mid-2010s, artificial intelligence could generate hyper-realistic images and defeat world champions at complex, rigid games like Go. Yet it consistently failed to understand a simple paragraph of human language. The problem was how the models read text. Older architectures processed words sequentially, one by one. By the time the system reached the end of a long sentence, it had often completely forgotten the context of the beginning. In 2017, a team of researchers at Google published a paper that introduced a completely new architecture, the transformer model. This diagram illustrates its core mechanism, called self-attention. Instead of reading left to right, the transformer analyzes every word in a sequence simultaneously. It maps how each piece of information relates to the others, instantly grasping the long-range context. Breaking out of that sequential trap was the final architectural hurdle. It allowed these models to process data at massive speeds and accurately map the structural complexity of human thought. This new architecture allowed for massive growth. Between 2018 and 2022, developers built large language models by training them on hundreds of billions of text parameters, resulting in a vast expansion of linguistic ability. This massive scale gave rise to an unexpected behavior called few-shot learning. By observing just a handful of examples, these models could successfully perform highly complex tasks, like writing software code, that they were never explicitly trained to do. As the technology moved from academic laboratories into everyday commercial products, it became a major target for international regulation. Governments quickly drafted new laws to ensure these highly capable systems remained safe and aligned with human intent. To move beyond simple text prediction, researchers began using reinforcement learning from human feedback to teach models how to follow complex instructions. The latest systems now use inference time scaling, meaning they can generate internal reasoning traces to double-check their own logic before they provide an answer. This shift has created agentic AI. These are autonomous entities that don't just respond to prompts. They can self-correct, plan multiple steps, and pursue real-world goals independently over long periods. The trajectory from a single mathematical neuron in 1943 to autonomous agents today suggests that the barriers to building machine intelligence were primarily architectural. As those hurdles fall, the 80-year effort to build an artificial mind is moving from a theoretical curiosity into an active engineering reality.